name is Bleak, and I'm going to be covering over the investigation of scouring in sticky soils or cohesive soils. So the summary of this research is to predict the maximum depth and contractions for scouring under pressurized flow, as well as be able to make models to test out the scouring with different flood conditions, as well as be able to, uh, you know, conduct different flow conditions and different soil properties, and as a result, be able to improve our models and predict scouring in different bridge designs. So, a quick background is that bridges are very, very vital to our transportation systems, and they get affected the most by scouring. And about 6% of the actual bridge failures in the U.S. are due to scouring, and they're even more increased whenever there is a flood. And due to this, we are wanting to cover uh, this this topic. And so our experimental setup is controlled in a laboratory environment and uses a 16-foot flume that's 2 foot in width and 1.5 in depth. And so essentially, we gather a specific amount of clay, uh, pour in some water, like it's a optimal moisture content, and with that we spread it, and then once we spread it, we're able to put it into the flume and basically tamp it, and so it's well compacted, and then we just start taking data like depth and velocity. So here we actually have the whole setup. So the water comes down here from the sump pump into the flow control valve, goes into this inlet tank, and goes down. And this is our ADV and speed laser, so they just control, or they get the velocities in various different directions. And here's even our clay right here, our soil box here. And here's an actual picture of it. So the water will come down here, have the soil right here, and it comes down here. And here's our ADV and our speed laser. You can see as a side view here. And here's also the points. So these points are like bed elevations, and then we'll take velocities at these specific points, and even the bulk density at very, very specific points. Oh, and the flow rate here too. So there's also, there's various parameters being investigated. So for our flow, we have our induation ratio, our proximity ratio, and our frutal number. And those play a very, very key role because in the next slide, I'll show you why the proximity ratio is really important. But you can see here in this diagram that we have the height of the water, we have the velocity, the discharge, which is the water moving through here, and our littoral deck here with the different equations here as well. And so, so currently we have three tests, right? So with each test, they're all pretty much the same, except that the proximity ratio changes in these ones, and they all use clay as well. And for our first test, this is within a 40-hour span. You can actually see that for a proximity ratio of 5, you can kind of see it change here. So you have the initial bed here, and then you have the bed after 40 hours. But what's crazy is that if you go to the next one, the proximity ratio is lowered at 3.5, but there's such a big difference here. After 10 hours, it hasn't even been 40 hours. It's only been 10 hours. So you can kind of see that change here from the initial to the final bed profile. So these two here, uh, our our expected outcome in this research is to essentially be able to make equations that will be able to calculate scour and make guidelines for estimating scour depths. So from this, we want to be able to determine, uh, formulas and ratios to be able to determine this, as well as any unique flow characteristics within the bridge, within our bridge deck, and also have better insights into time-dependent scouring. And that's all. Thank you for watching, and I hope you have a great one.